In example 1 we have this problem. We have an outer circle here, the outer boundary, which is centered at 0 and with radius equal to 1. And we have some other circle with center at 2/5, this point, and with radius 2/5. And we know the boundary conditions on this circle, which is equal to 110, and on the outer circle, which is equal to 0. So, well, we are now going to find another domain which is more easy to where it's more easy to calculate the solution of our problem. So this is done by a conformal mapping, and we know that there exists a Möbius transform. In fact, this transform, where b is some real number with absolute value less than 1. Actually, we can use any complex value with absolute value less than 1, but it's enough for us in this case to consider real values of b. So having real values of b, we see that any point on the real axis, that's when z is a real number, will be mapped onto this region d star with somewhere on the real line. And why is this a real value? Yes, it's easy to see. If we have used a real value on b and we have real value on z, then this cannot be other things than a real number. Not they cannot have any imaginary part. So this means that since the center of this circle is on the real line, this means that these 2 points must be mapped either onto this point or this point. So what we are going to do now is that we assume that this point is mapped onto this point, and this point is mapped onto this point. And by using this, we can find the radius of this circle, which is called R0, and we also can find the value of b. So then we know this conformal mapping, transforming this region, complicated region d, onto this more symmetric region d star, where we can find the solution. In fact, we have solved this problem earlier when we have symmetric circles. So let's find this value b. First, we start with mapping this point onto this point. Well, we put z equal to 0, and we let w be equal to r0. So R0 is now, we start with this point and map it onto this point. We have already said that this should be the w value, which is equal to R0, but R0 we don't know yet. Similarly, if we map this point onto this point, then we must choose the z value here, which is equal to 4/5. In order to see this, it's we know that the center here is 2/5, and it's this point is then equal to the double value of this. So z is equal to 4/5. And we insert this value into this Möbius transform, and we also insert this z value into this Möbius transform, and we are mapping it onto these 2 values, w equal to 0, r0, and w equal to minus r0, because they are on opposite places relative to the center of this circle. So doing this, we obtain two equations. We put set first equal to 0 into this expression, and we know that w should be equal to r0. Similarly, we do the same here, and then we get two equations. In fact, this is very easy to compute. We know that this equation means that b is equal to r0. So then we know this condition, and putting b or r0 b in the expression equal to r0, we obtain this identity, this equation, and multiplying here with 5 on both sides, we obtain this equation. And this equation is very easy to solve by multiplying now with this term on both sides, and this gives us a second order equation which is very easy to solve. We obtain two solutions, r0 and r0 is equal to 2 and 1/2. And we said earlier that we should choose values of b which has the absolute value less than 1, and therefore we have to choose 1/2, 1/2. So r0 is in fact equal to 1/2. So now we know this Möbius transform. We have found the value b, and in fact we also have found the radius r0. So we know both of this. Well, the Möbius transform takes this form. We can multiply with 2, and then we get a more simple expression. So we have now this conformal mapping, and we are almost there. We only want now to find the solution in the problem in the D star region. And how can we find this solution? Well, it's done here. We know that the complex potential is given by this expression. It is done earlier, and A is some constant and B is some constant. And in fact, the real part of this complex potential is what we are looking for. We are looking for phi star, which is on this form A multiplied with the logarithm of the absolute value of W. So what we are now going to find is the value of A. In fact, we have to find the value of B also. Here we have it. We know that for the absolute value on the outer circle, which is given by the absolute value of W equal to 1, the solution should be equal to 0. Let's go back and verify this. So on the outer circle here, the potential is equal to 0. So therefore, when the absolute value of W is equal to 1, which we insert here, we know that the solution is equal to 0, and we just insert these values for the absolute value of W and for this total expression. So the logarithm of 1 is of course equal to 0, so this term vanishes, so we conclude that the B is equal to 0. So it remains to find the value of A. Well, the value of A is found by knowing that on the inner circle, which has the radius equal to R0, which we have found was equal to 1/2, then the potential is equal to 110. Let's go back and just see this. So on this inner circle with radius R0, which we have computed is R0 is equal to 1/2. On this circle, the potential is equal to 110. So let's insert this information into this expression. So we have that A multiplied with the absolute value of W, which was 1/2. The radius was 1/2 plus B, which we have seen is equal to 0, should be equal to 110. So then of course A must be equal to this guy over the logarithm of 1/2, and it's easy to compute. It's minus 158.7. So now we have this expression. It's actually equal to minus this guy multiplied with the logarithm of the absolute value of W. And what we learned in the general theory is that the potential phi, which is the solution we are looking for, is just this phi star of uv, where we replace u and v by the real part of the function f of z and the imaginary part of this function f of z. And we know here that this is equal to this expression, but we know also that w is we should replace w by just f of z, and f of z was this. We have computed that it's this expression. So what we end up with here is the absolute value of this expression in terms of z, but z is also described by x and y, so we can also describe this function by x and y, but this is more complicated. It's easy for us to do if we just multiply this with the complex conjugate, both in the numerator and denominator. Then we can find this absolute value, but it's a more complicated expression which we do not need to do at this time.